Hello, hello, hello. In this episode of What's the Big Idea, we're going to talk about potential energy. Potential energy is an essential idea if we're going to extend our discussions of energy to deal with systems that are more complicated than single particles. So let's dig in. So, our basic approach to energy problems is to divide the world into a system and its surroundings. And the energy principle says, with suitable definitions of energy and work, it will be true that the change in the energy of the system can be calculated by calculating the work done by the surroundings on the system. So to date, we've talked about a system that consists of just a single particle. So if we have a one particle system, then we've shown that the right way to define the energy of such a system is in terms of the kinetic energy of the particle, which is just one half the mass of the particle times its speed squared. And if you do that and your system consists of a single particle, then we are led to the work kinetic energy theorem, which the change in the energy of the system is just the change in the kinetic energy of the particle, and that will be equal to the work done on the particle by the surroundings. So now it's natural to say, okay, well, we had success there. The next step up is to consider not a one particle system, but a two particle system. So imagine that your system consists of two masses, which we'll call M1 and M2. And then the natural question is, in this case of a two-particle system, what is the correct way to define the energy of the system? Well, it would be natural to guess that you should just simply add the kinetic energies of the two particles. So that's one possibility. So if this were the right way to define the energy of the system, then we could calculate the energy of the system. We would write it as 1 half m1 v1 squared plus 1 half m2 v2 squared. Okay, so is that a reasonable way to define the energy of a two-particle system? Well, there's a problem with that definition, which I can show you with the following argument. Um, suppose our two-particle system is isolated. And by isolated, I mean that there is no significant interaction with the surroundings. So an isolated system, sort of by definition, if it's not interacting with the surroundings, the amount of work being done by the surroundings on the system has got to be equal to zero. Okay, so what does that imply? Well, the energy principle then states that the change in the energy of the system has got to be zero. If there's no interaction with the surroundings, then there can't be any change in the energy of the system. And that's another way of saying what we've called the conservation of energy. If you have an isolated system, then the total amount of energy in the system is conserved. It remains unchanged. So the problem arises from the fact that when you have a two-particle system, there's the possibility that the two particles can interact with one another. And a famous example, which we'll study a lot in this course, is the gravitational interaction. There can be a gravitational interaction, gravitational forces that exist between the two particles that make up your isolated system. So, for example, suppose the two particles that make up your isolated system are the Earth and an apple. And the apple, suppose initially uh, they're at rest, and it's an isolated system, so there's no kinetic energy in the system. And then the apple starts falling towards the earth, and in fact, the earth will move a little bit towards the apple. But they each gain some kinetic energy, and whereas you started off with no kinetic energy, as they fall towards one another, they each have kinetic energy. Kinetic energy is a positive quantity; it can't be negative. So if the energy of this two-particle system was simply the sum of the kinetic energies, we would violate the conservation of energy. There's no interaction with the surroundings. The total energy can't change. If the particles are each gaining positive kinetic energy, then the books are not balanced. The total energy of the system would be increasing with this definition of the energy of the system. And that means that this definition can't be correct. We need to modify our definition of the energy of the system. It's got to be more than just the sum of the kinetic energies of the individual particles. So to solve this problem, we're going to do some creative bookkeeping. As I keep saying, dealing with energy often feels a lot like doing accounting, and we're going to balance the books by doing some creative bookkeeping. So we're going to modify our definition of the total energy of this two-particle system to get the books to balance. So we're going to start off by assuming that the energy of our two-particle system has contributions from the kinetic energy of the apple and the kinetic energy of the earth. But now we have to add to that something, we don't quite know yet what, such that as the apple falls towards the earth, the total energy of the system remains unchanged, so that the conservation of the principle of conservation of energy remains satisfied. And that something is going to involve this new concept, this new form of energy, which we're going to call potential energy. So let's see how that works. So as the apple and earth fall towards one another, we know that the apple is going to gain a kinetic energy. So delta K sub apple is just going to be equal to the work done by the earth on the apple. And why do we know that? Well, that's basically just the work kinetic energy theorem, right? We're treating, in this case, we're thinking of the apple as the system, and so it's got to be true that the change in the kinetic energy of that one particle apple is just calculated by the work of the only thing that can do work on the apple is the earth in this problem. There's nothing else in the world. So that's how we calculate the change in the kinetic energy of the apple. Similarly, the change in the kinetic energy of the earth has got to be given by the work done by the apple on the earth. And so now to balance the books, we're going to introduce this new concept of potential energy. And we're going to define how the potential energy of this particular system changes. We're going to define changes in the potential energy of the Apple Earth system in the following way. I just, again, just to get the books to balance, we're going to say that the change in the potential energy of the Apple Earth system is given by, well, it's minus the sum of the work done by the Earth on the apple and the work done by the apple on the Earth. And now we're going to consider that the energy in the system consists of both kinetic and potential energy. So that means that if we want to calculate changes in the energy of the two-particle system, we need to add the change in the kinetic energy of the system plus the change in the potential energy of the system, and the change in the kinetic energy of the system is just the sum of the change in the kinetic energy of the apple plus the change in the kinetic energy of the Earth. And if you look at the way we've defined, excuse me, the change in potential energy of the system, you can see that we've rigged it so that the change in potential energy of the system, because of this minus sign, is just going to make this whole thing add to zero, right? Because of this minus sign here, if you plug in W by the work done by the Earth on the apple, that gives you a delta K apple. And if you plug in the work done by the apple on the Earth, that gives you delta K sub Earth. And then this minus sign means that when you add it all together, you have a delta K apple plus delta K Earth minus delta K apple minus delta K Earth. So the whole thing is ingeniously rigged to give zero. And so now we have a new language that we can use to describe what happens if the apple and the earth are initially at rest and they start falling towards one another. The kinetic energy of the system must be we've argued has to be increasing, but there's a new type of energy called potential energy, which is decreasing by just the right amount so that the total change in the energy of the system remains zero throughout the motion. Okay, so now all that remains is to calculate how the potential energy of this particular system has changed. And we're assuming that, let's assume for the purposes of this calculation, that the apple starts off an initial height h sub I above the Earth's surface, and then in the final state, it has fallen to a state h sub f above the Earth's surface. And let's assume that the force of gravity in this case is just constant and is just equal to m times g as usual. Now, as we've said before, strictly speaking, the apple's going to fall towards the earth, and the Earth is also going to fall towards the apple. But because the Earth is so much more massive than the apple in this story, the Earth is going to move very, very little. And so the work done by the apple on the Earth is going to be negligible in this particular example because the force is modest and the Earth doesn't move very much. So the work is a force times an infinitesimally small movement. We can ignore this term. And the change in the potential energy of the system is just equal to minus the work done by the Earth on the apple. And of course, that work is positive. The apple is moving in this direction, and the force of gravity is in the same direction. So the work done is positive, but then there's this minus sign out in front that makes the change in the potential energy of the system negative. So it's minus, and the work done is just mg times hi minus hf. And now we recognize that hi minus hf is just minus delta h. So there are two minus signs here, and we can write in the end that the change in the potential energy of the system is just mg delta h. So in the story, delta h is negative. The height is decreasing, so there is a decrease in the potential energy of the system as the apple falls towards Earth, and that exactly offsets the gain in the kinetic energy of the system. And you'll notice I keep saying the potential energy of the system. You'll often hear people who are being a little bit sloppy about it talk about the potential energy of the apple. But really, as this derivation makes clear, the potential energy really is a characteristic of the entire two-particle system. So it's much more correct to talk about the changes in the potential energy of the apple-Earth system. So, as a concrete example of how this all works, let's try applying this to the how fast is the pendulum problem. We'll assume that the pendulum starts at rest at some height y I above the bottom of the arc here. So we're defining a y-axis here, and we've assumed that the origin of the y-axis is right at the bottom of this circular path that the pendulum is going to swing upon. And let's use our energy principle and our newfound language of potential energy to describe and solve this problem. So we're going to we have to define our system, and we're going to include our system and define our system so as to include the Earth. And so that means we're going to draw our dotted line around everything. So this is going to be an isolated system, and therefore we expect that the change in the energy of the system should remain equal to zero. Energy is conserved, and that way we calculate the total change in the total energy of the system is to add up the changes in the kinetic energy of the system and the potential energy of the system. Those must add to zero. And since the system starts off with zero kinetic energy, the change in the kinetic energy of the system is just equal to 1/2 whatever the mass of this bob is times its final velocity squared. And by final velocity, I mean the velocity when it reaches the y equals 0 point. And the change in the potential energy of the system, we said, is going to be equal to mg times the change in the height. And the change in the height, it's going from an initial height of yi to a final height of 0. So the change in the elevation is minus yi. And that's got to sum to 0. So this says, just rearranging, this says that 1/2 mv final squared is equal to mg times the initial value of y. Clearly, the m's cancel, and the final speed of the pendulum is equal to the square root of 2g times yi, which is what we've previously found from the work kinetic energy theorem. But the language of potential energy is a very convenient language, and we will extend this notion of potential energy very, very broadly as we proceed to discuss energy. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.